Non-destructive testing. Ultrasonic examination. The basic principle of ultrasonic testing of materials is the propagation and reflection of sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section through the cylinder shows the position of the atoms extremely magnified and simplified as a single crystal. To begin with, a rigid unyielding stop is attached to the right front end of the cylinder. At the left front end, a disc is installed. It will be used to transmit and receive sound waves. Pushing and pulling briefly at the disc causes a longitudinal sound wave to propagate through the cylinder. When the sound wave reaches the rigid stop at the right side, it is reflected and runs back towards the disc, which now serves as a receiver. A free end is also able to reflect a wave. In this case, however, the tensile side runs ahead in the reflected wave and finally deflects the receiver to the right. The reflected wave is even reflected again and actually travels for several times across the length of the cylinder, but this is not shown in the animation for the sake of simplicity. So, if a sound wave is generated at one end of a workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound wave is reflected and it returns to the transmitter, which then acts as a receiver. For ultrasonic testing of a workpiece, not a large transmitter is used in most cases, but a rather compact one, which generates a short ultrasonic pulse. At a place free from defects, the ultrasonic pulse travels to the right front end, also termed back wall. The pulse is reflected and recorded again as an echo. When the transmitter is moved a little downwards, the cavity reflects a part of the wave. That part arrives earlier at the transmitter than the rest of the sound wave. Even further downwards, the cavity reflects the complete ultrasonic pulse. For material testing, either the echo of a defect can be utilized, this is the pulse echo mode, or the phenomenon that hardly any sound waves pass through the imperfection. This is called the through transmission mode. In pulse echo mode, a transducer installed in a probe performs both the sending and the receiving of the ultrasonic pulse. On a computer monitor, the intensity is being plotted upwards on the y-axis and the time towards the right on the x-axis. With the probe at a place free from defects, only two signals may be seen on the monitor: the transmission pulse and the echo resulting from the lower surface of the workpiece, termed back wall echo. Moving the probe towards the right leads to an additional echo created by the defect. Even further towards the right, only the defect echo is visible apart from the transmission pulse. In our laboratory, there's a green painted steel cylinder to be found. It contains artificial defects which are invisible from the outside. To track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder. Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time. A very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 mm below the probe, so the cylinder has a height of 200 mm. And here we go. The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 mm below the surface. Another echo indicates a defect in a depth of 87 millimeters. The second, smaller echo at 174 millimeters is caused by double reflection on the same imperfection. And these are the defects. A drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 millimeters. The saw cut 87 millimeters below the surface. Trams are popular means of transport in Karlsruhe in southern Germany. The tram cars are not only cleaned regularly, but also tested thoroughly in regular intervals by the transport company. Among many other maintenance points, the ultrasonic examination of the wheel axles plays an important role. A tram enters the maintenance hall for inspection. Some of the tram cars have already been lifted up. That way the bogies can easily be detached, pushed forward and examined carefully. This is one of the bogies jacked up to comfortable working height and prepared for ultrasonic inspection. Special attention is given to the wheel axle, among experts known as wheel set axle. It has been designed as a hollow axle. This saves weight and facilitates the ultrasonic examination. The material tester applies a suitable oil as a couplant into the bore of the axle. Now he takes a special probe designed exactly for this purpose, inserts it carefully into the bore with a mount, and evenly spreads out the couplant by turning and pushing. He has accurately marked the most important examination points at the mount. In an experienced manner, he positions the probe at the appropriate places within the wheel set axle and watches the monitor closely. The probe has specially been designed for this application. It transmits the ultrasonic pulses at an angle of 45 degrees. At a place without defects, no defect echo returns. But when the pulse encounters a crack which has grown in from the outside, double reflection occurs and a typical defect echo is recorded. It is important to note that also the shape of the wheel set axle may lead to an echo, for example at shoulders. These are so-called contour echoes. In this particular case, only contour echoes are recorded. No abnormality has been detected. The wheel set axle is perfect and can be used again to transport many passengers until the next examination becomes due.